Hello everyone, I'm Siddharthan. Currently we are in the first module of our deep learning course, and in this first module we are discussing about the basics of deep learning and neural network. In the previous video we have seen how we can build a sigmoid perceptron from scratch in Python, and in this video let's try to implement this perceptron using a sample dataset. So that will be the topic for today, and let's get started. So before trying to implement this code, I just wanted to mention one thing. So in the last video that we have worked on, there is a slight issue in the code. So if you remember, we have made this evaluation function. So in that, so I have put this accuracy formula and this return statement within this for loop, but it should come outside of the for loop. So maybe you can like make this change in the code as well. So you will find the link for this notebook in that video's description, so I'll also make this change in that file. So now we can get started. I'll also give you a quick recap on what is meant by this functions that we have and this sigmoid perceptron. So first I'll import numpy as np, and now let's copy this sigmoid perceptron class that we have built, and let's paste it here. Yeah, so let's try to understand this quickly. So here we are creating a class called a sigmoid, and here we have 5 functions. First is the init function, where we are initiating our parameters, and this input size is nothing but the number of input features that we have in our dataset. Or you can also think about this as the number of columns that you have in a dataset. So the user will pass this while calling the sigmoid perceptron class, and here we are randomly initiating the weight value and bias value using np.random. So the next function is sigmoid, where we pass this weighted sum, which is the z, to the sigmoid function to get the value out of this. So this will be the output of the sigmoid perceptron. So we apply a sigmoid function so that we get the value between 0 and 1, okay, just like a probability value. And then we have this predict function, where we pass the inputs, and this predict function will give you the weighted sum, and this weighted sum in turn will be fed to the sigmoid function that we have created. So it's basically calculates your weighted sum and applies the sigmoid function to your input data. And this is the fit function, where the training of the perceptron model happens, and the input parameters for this fit function are your inputs, which is input features, and then you have targets, which is the labels for those corresponding inputs, and then you have two hyperparameters, learning rate and number of epochs, which we can set. And now you have the number of examples, which represents the total number of data points that you have, and this is number of epochs is the number of epochs or the iterations on which the model is going to train. And in each epoch, when we work with each example, each training example, we try to make the prediction from the model, and this will again find the error, and it will like calculate the gradients, and it will update the weight and bias using this particular gradient. So this is how the gradient descent optimization works in this perceptron code. Okay, so once this fit function happens, you would get the most optimized weight value and bias value that will give you the least error possible. Okay, and then you have this evaluate function, where you can pass the input features and the target. So this will basically give you your accuracy value. So this is the code. As I said, you just need to make this change, where this accuracy and return statement should come outside of this for loop. Okay, so it shouldn't come inside of the for loop. So that's the other thing. Now I have this diabetes dataset uploaded here, so let's work on this. I hope that you have already worked on this. So let's take this dataset, and let's try to train the sigmoid perceptron that we have built. Okay, so first I'll just create a text cell here, and I'll call this as importing the dependencies. Okay, so first let's import pandas as PD. So we have already imported numpy, and then I'll import from sklearn dot model selection import train testplate. And then we can import our standard scalar from sklearn dot pre-processing import standard scalar. So let's run this. Now let's load our dataset. I'll also give the link for this diabetes dataset in this video description. You can download it. So here I'll load this as df is equal to pd.readcsv. So here you can mention the path of the file, which is diabetes.csv. Let's run this. It's also print the it. So I'm not going to do a very detailed data processing and all those things. Let's just like keep things simple, because the main scope and idea of this video is to show this implementation. Okay, so here I'll just find this outcome distribution. Let's see the value count. So this will show you how many ones and zeros are there. So now we are going to treat this as a binary classification problem, where the model can tell whether a person is diabetic or not. 1 means the person is diabetic, 0 means the person is like not diabetic. So in this outcome column, I'm applying this value counts. So let's run this. So this says that there are like 500 data points that has the class as 0 and 268 data points that has the class as 1. Now we could see that there is some imbalance in this data set. Now what I'm going to do is I'm going to take 268 data points for 1 and I'm going to take 268 data points for 0. Basically I am undersampling the class 0 so that we have like even distribution of zeros and ones. So let's separate this. So I'll just create like two data frames here. Class 0 df is equal to, I'm going to filter this main data frame. This class 1 will go to one data frame, and this this class 0 will go to one data frame, and class 1 will go to another data frame. So let's see this. So this is how you can do this. So first you need to mention this df, and within this square bracket again mention this df, and now within this you can mention the outcome column, the column using which you are going to split it. So I'm going to say 0, right? So this will filter all the data points with 0 as the outcome. Similarly, let's create another data frame as class 1 df, and here the outcome should be 1. Now let's undersample this class 0 df. So this is 0, and now I'm going to say class 0 df is equal to, so you can mention the data frame name and use this function called as sample. So this will like randomly sample some number of data points. So here I'm going to say 268 because that is the number of data points that we have for 1. So we won't change any data points for class 1, but we will just like undersample this class 0 data points. So 268. Now I'm going to join these two data frames and create a new data frame called as data. Again, that can be like other simple ways to do this filtration and undersampling itself. So I'm just like using this particular method. So it's not like you should use this method alone. So this is how pd.concat works. So concat, we are going to like combine like these two data frames. So we have this pd.concat, and within this you have to create a list, and within that list put the names of these two data frames. One is class 0. So make sure like you are mentioning this parenthesis, make sure that you are creating this list within that, so then only it will work. So class 0 df and class 1 df. Okay, so I'll run this. Let's print the head of this data frame, the first 5 rows. So you have all the outcome as 0. So previously it was like not the case. Now let's print the tail. So that should contain all the outcomes as 1. Yeah, the first 5 rows and the last 5 rows. Let's see the shape of the original data frame. So it would be the sum of this. Let's print this one here, df dot shape. So 768 comma 9. So 9 columns are there, and here I'll say data.8. So this is like the undersample data. Sorry, this should be data.shape, right? Yeah, now this has like 536 even distribution of 0 and 1. So let's make sure the value counts is proper. So this will tell us whether the sampling has happened properly. So this df, change it to data. Yeah, so we have 268 zeros and 268 ones. Now we are going to separate the input features and the target separately. So these are my input features: pregnancies, glucose, blood pressure, skin thickness, etc. until age, and this outcome is my y. So I'm going to say x is equal to data dot drop. So I'm going to drop the outcome column alone and save all the other things in this x. Say outcome, and axis is equal to 1. So you can see here I'm not mentioning the in place, because in this y I'm going to save this data of outcome, right? So this will go, if you mention in place here, so this outcome column will be removed in this original data frame. So I don't want to do that. I just want to save all these things in one data frame called as x, and outcome in other data frame called as y. So that's why we are not mentioning this in place here. So we are creating x and y. So you can also try printing this. So before that I'll check this type of x. So here you can see it is in the form of pandas like data frame object, so you can print this x and y and c. But I need the values to be in a numpy array. So this is in a data frame. Let's convert this to numpy array. So it's better to feed numpy arrays to our perceptron model. So for that, you can say x is equal to x dot values. So this will extract all the values and put it as a numpy array. I'm not renaming this. Let's have the same name, x and y values. Now you can check the type of your x. It should say numpy array. Yeah, numpy n dimensional array. And now you can print your x and y and z. So now you don't have those column names, you just have an array. Similarly for y as well. Yeah, so this is how you can convert these data frames into numpy arrays. The next step is performing train test split. So after performing the train test split, we can apply the standard scalar. So let's call this as train test split. So here we are going to have like 4 arrays. So those arrays will be x train, x test. So this order shouldn't change. Y train and y test. X train, x test, y train and y test. And this is equal to train test split. So this we have already imported in our import statements. So here I'm going to say x and y. So we have to separate x and y as training data and test data. Let's take the test size as 0.2, 20%, and stratify is equal to y. I'll explain you what is meant by the stratify. Random state, you can take any values. So I'm going to take, let's say 42, the usually used value. Let's try to understand this. Okay, so here we are creating 4 arrays: x train, x test, y train and y test. X train is your training data input features, and the corresponding labels for this training data is stored in y train. Okay, x test is the test data features, input features, and the labels for those test data will be stored in this y test. So basically x represents your input features and y represents your label. So we are using this train test split. So we are getting these 4 arrays from these original arrays, which is this x and y, and test size 0.2, which means 20% will be your test data and remaining 80% will be your training data. And stratify, so stratify is equal to y. Make sure that it kind of training data and test data as a even distribution of your 2 labels, 0 and 1. Okay, so what happens is there is a chance that let's say 20% of data, let's say that we have 1000 data points in our original data set, and so 20% of that, 200 will go to your test data and 800 will go to your training data. So if you don't mention the stratify, there is a chance that out of those 200 test data, like 180 data or 150 data may contain the class 1, or it may contain the class 0. So there is this possibility of imbalanced labels going to one of the training data and test data. So we don't want to do that. So that's why we are having the stratify. So it makes sure that we get a uniform distribution and this random state. So each time we run this train test split, it will split the data in a random way. So you won't get the same data all the time. So it would split the data in a different way. And mentioning the random state number gives us that reproducibility option. So if you are using the random state as 42 as well, your data and my data will be split in the same way in this particular notebook. So if you're using a different number, then your data, your training data and test data will contain like a different distribution of data. So that's the main idea, which is random state is mainly used for your reproducibility. Now let's apply our standard scalar. So here you can see I'm not performing the standard scalar on my entire data, because what happens is there is a chance that this doesn't happen always, but there is like a good chance for this happening. If you perform standard scalar before train test split, what happens is you're scaling your you're basically scaling the data based on your like entire data. We don't want that. So the ideal way would be to scale your data on x train and use that same scalar for the x test or your test data scaling. Okay, so this is mainly to avoid a problem called as data leakage. So what happens is when you do that, there is a chance that the model knows how the test data is going to be or how the test data will be, because you have already scaled the entire data together. So we, in order to avoid that, what we would do is first we would split the data into training data and test data, and later we perform the scaling operation. But in these like basic data sets, there won't be any change in the accuracy value that you would get. But the ideal way is to do by this way, where you first split the data into training data and test data and later apply the scalar. So I'll create this scalar variable. I'm going to instantiate standard scalar. So we are having this instance of standard scalar. Now I'm going to create two variables. One is xtrain scaled is equal to scalar dot fit transform xtrain, and then we have x test scaled. Make sure that you are not fitting and transforming it, just transform it, and then you have this test data. So how this works is we are first loading the standard scalar function. Now we are fitting the training data and transforming it to get the standard scaled data, and now we have this x test scale. So here you shouldn't perform the fit transform. So this transformation should happen based on the fit that you add with your training data. So this is how you basically do your standard scaling operation. So I hope everyone knows what this standard scalar operation does, but I'll explain you this. So we need the data to have a uniform normal distribution. So sometimes like your data may not have it. So what happens is like we need the data where the mean value of this data is 1 and the standard deviation of the value is 0, right? So that would be the proper normal distribution that we would expect, but this may not be the case when we add this original data set. Okay, so that's why we perform the standard scalar so that we have this data in a proper distribution. So yeah, that's the idea for doing this. There is other way, there is like some other transformation called as normalization that won't take these things into consideration. So what happens is it will basically transform your data such that all the columns are in the same kind of like same range. So that process is called as normalization. So one of the methods is MinMax Scalar. So what happens is here you can see we have pregnancy values. Here the values are like 10, 21 something and so on, and glucose values is in hundreds, blood pressure values 80, 70, 60 and so on, skin thickness is 37, and BMI is 35, 22. So you can see that all the columns have data in like different ranges. So we don't want that to happen. So what happens is like if that's the case, if a particular column has like a range that is larger, let's say it has values between 200 to 500, the model may think that this is an important feature. So we don't want that to happen. So for that purpose we apply normalization that will kind of transform all the data into where like all the columns have data between 0 and 1. So that's called as min-max scalar. So I mean you can set what's the maximum value and minimum value that you want, but yeah, the data should lie between 0 and 1. So there is like no issues in the unit of column. So all the columns will have the value between 0 and 1. So that is one type of data transformation, and the other type is standardized. So we call this as standardization. The other thing that I explained to you is called as normalization, but yeah, standardization is better when we compare it to normalization. So yeah, I think yep, that should be enough for this particular explanation. Now we can go on and train our perceptron with this scale data. So for this, first I have to load this class called as Sigmoid Perceptron, and then I will call this fit function. Later like I can call this evaluate and see like what's the performance of this model. So here I'll call this as Sigmoid Perceptron because we are using a Sigmoid activation function. So let's call this variable as, let's say, Perceptron. You can call model or Perceptron or like basically anything. So I'll call this Sigmoid Perceptron, and the input values that we have to give here is my basically my input size. Okay, so these are like randomly initiated, so we don't have to worry about this, but this we have to give, which is this input size. So let's come back here and say input size. Again, as I said, it's nothing but the number of columns that you have. So I mean the reason for having this is like we should have the same number of feet, so that's why we basically need this. So I'll say input size is equal to xtrain scaled dot shape 1. Okay, so we know that this data basically contained like 9 columns, and one of those columns is outcome. So your input shape or the number of columns in your training input features is 8, but I don't want to give like solid number, because like next time you're training with a different data set that may have a different column name. So that's why I'm not like straightly putting 8 here. So you can also like check this. I can xtrain scale dot shape of 1. So if you print this, you would get 8 as the value. So that is what we are having here. If you have a data set with 100 columns, in that case we would have like this 100 as the thing, right? So if you basically print this shape alone, this will give you 428, which is the number of rows, and 8 as the number of columns. But we are more interested in the number of columns, which is the number of input features that we have. So I'll say shape of 1, which is the second value of this tuple, which is 8. So here you can mention this xtrain dot shape of 1, and this will like create an instance of the sigmoid perceptron. Now we can train the perceptron model. So train the perceptron model. Here I can say perceptron dot fit. So here let's see what are all the input features that's required. So first you need to, yeah, self is nothing but the variable, the perceptron that we are loaded, so it's nothing serious, right? So we need to give these input features. First is your inputs, basically your input features. Targets is your label, learning rate, and number of epochs. Let's give like these 4 things. I'll just copy this. Let's come back here, or I think you can just mention this alone. You can just mention like those data alone, or you can say inputs is equal to xtrain scale. So both should work, and yeah, it's up to you. And targets will be your white train. Okay, and learning rate, let's give the learning rate as 0.1. I mean, you can use 0.01 or any learning rates. I'm going to use 0.1. And number of epochs, let's say that we are having like 100 epochs, so which is basically the number of iteration. You can also take like even 1000, so it shouldn't take like that much computation, as this is like a very small data and a simple model. So this is where the fitting happens, or the training happens. So what happens here is, when this fit function is called, we basically have a random weight value and random bias value. So weight is basically a vector that contains random values, so that weight would basically have like 8 values, okay, because it is equal to the number of features that we have. And your random bias value will be generated. So with this random weights, it will again make the predictions by passing in this data, and at each step it will try to update the weights and bias to see if it's kind of achieving a better performance. So this thing happens through these 100 epochs, and we change or update the weights and parameters for like each data point. And once that training is happened, so let's run this. So that's what happens when we execute this particular line of code. Now you have a trained model once this has like completed running. Yeah, so this is completed, so this is a trained model. Now you can say yeah, the next step is like evaluating the model. So I'll call this as model evaluation. Yeah, let's call this as model training. Okay, so now we are going to call the evaluate function, and we can also see the input parameters required. So the input required are your input data and target. So this will again call this trained model, which is this, yeah, self, and it will call this predict function, and it will make the prediction, and this will be in further compared with the original target. Okay, so if the prediction, if the sigmoid prediction is more than 0.5, it will say the class is 1. If not, it will say it is 0, and then you have the, of course, the accuracy score will be returned. Now let's run this. So here I'm going to say evaluate the model for training data. So I'm going to do the evaluation for both training data and test data to make sure if there is any overfitting happening or not. So training data, so later let's do this for test data. So I'm going to say accuracy is equal to perceptron dot evaluate the xtrain scaled comma white train. Okay, so this will calculate that accuracy. Now you can print this as training accuracy is equal to accuracy. Let's run this. Let's see what's the accuracy. So we are getting almost like 76.1 percentage. I mean, if you want, you can also multiply this with 100. Maybe, yeah, let's do that. So accuracy is equal to let's multiply this with 100 and round it to let's say 2 decimal points, round accuracy into 100, comma 2. Yeah, this should work. Let's see, this should give us 76.17. Yeah, so let's maybe add a percentage symbol here. Yeah, so basically we are taking the accuracy which is in the form of decimal between 0 and 1, and we are multiplying it with 100 and just taking, like, this is rounding, so that's why I have this. If I have 1, you will get like only one decimal value, and we are just printing this as training accuracy. So this is training data. If you see this, let's do the same for test accuracy as well. So I need to change this to test. So if you remember, we have transformed this test data. Let's call this as white train, sorry, white test, and this should be test accuracy. So both the training accuracy and test accuracy should be closer. Yeah, we are getting the test accuracy as 72.2 percentage. So there is that, we don't seem to have a overfitting issue. Overfitting is the issue when your training data is very high compared to your test data, and there is like a very huge difference between them. So that's what we call as overfitting, but thankfully it's not happening. But still the accuracy is lower because we know that this is a very simple model. Again, you can try it with different hyperparameter values, you can like do some better data pre-processing, but you may not get like very high accuracy because, as I said, this is a basic model. So if we go to deep learning, so that's when we have like several combinations of this perceptron, several layers that kind of solves like a lot of issues. As we know that perceptron is also, it can't work well on linearly separable data, so those what we can say issues are there, right? So that's one thing. Yeah, but implementation wise, this is a good thing. As I said earlier in the previous video as well, we are not like looking mainly for the accuracy but for the implementation. So I hope everyone is clear with the data processing and the implementation that we did. As the next step, what I'll do is, let's put this class in a separate .py file and let's try to import it and use this as a Python class. Okay, so I'll just open my notepad plus plus. So here we need to create this .py file. You can either use notepad plus plus, or even you can use your Visual Studio Code. VS Code can also be used. So first maybe I'll import numpy just to be sure. Import numpy as np, and let's paste this class code. Yeah, Sigmoid Perceptron code. So I'll show you how you can import this as well. Yeah, now maybe you can add some doc string to this explaining like what this object will do, so I'll leave that up to you. Now let's, yeah, save this. I'll maybe save this to my desktop. So I need a Python file. Yeah, here it is. So I'll call this as Perceptron class. Okay, yeah, Perceptron class dot py. Let's save this. Okay, so now we have a .py file. Now we can upload this .py file to another environment and see how we can do like all the other things that we did. Okay, so I have already, yeah, I have this diabetes data. Let's see how we can upload this file and do all the training and evaluation part. So I'm going to upload this .py file. So it's in my desktop. So Perceptron, yeah, Perceptron class.py. Okay, now what we can do is, let's import numpy. I mean, you don't have to import because it's already getting imported in this .py file, but anyway, I'll do this. Now from Perceptron class, Perceptron class is nothing but, so it will look for this like .py file. So Perceptron class import, give the class name which is the Sigmoid Perceptron that we have created. So this class name, maybe I'll copy this from here. Yeah, let's run this and see if this works. Yeah, so this has imported well. Now we can do like all the other steps. So we don't need this code anymore because we put together this in a .py file. So I'll just like copy this entire thing. Yeah, and let's paste it here. Okay, so this should be Sigmoid Perceptron dot fit. So here we should first create an instance. Yeah, this should probably work. Let's check this. The basic data processing, standard scaling, train tested, those details. Let's see if we are getting like the same value in both the cases. Yeah, we can see. So yeah, there seems to be a difference in the training accuracy. It can be because of the gradients that we are using. There can be like some other random state issue, but yeah, the values are like almost similar as we got before. So let me just check. Yeah, so the training accuracy is same. The test state accuracy is like a bit different. Yeah, it's not a big issue. Okay, so this is how you can put this Perceptron class that we have created in a Python file, and like you can import this, and like basically you can use it for like a different data set. So I hope everyone is clear with the things that we have done here. And yeah, that's it from my side for this video. I'll see you in the next upload. Thanks for watching.